Swayam Prabha. Digital India. Educated India.
Welcome back, friends, to another session of fluid mechanics and rate processes. In the last session we looked at the potential flow past a circular cylinder and how it gets modified when the flow is viscous. If you remember, in the potential flow for a circular cylinder, we were able to see that it generates neither a lift force nor a drag force. Is it possible for a cylinder, even in a potential flow, to generate any force? We are going to model this flow now using the addition of a free vortex. So let's start looking at it. So first we would like to review what we did for a stationary cylinder. Let me recollect for you the potential flow. This was given as a potential. It was a combination of a doublet kept in a uniform flow, and we were able to simplify this to 1 plus r square by small r square cosine theta. Similarly, the stream function was given as u times r 1 minus r square by small r square sine theta. Let me recollect the streamlines for you. So if this is the circular cylinder and that's the origin, I am only going to draw the streamlines outside the cylinder. So this was the stagnation streamline. The surface of the cylinder is also a streamline, and then the flow looks something like this. Okay. We were able to identify two stagnation points, S1 and S2. At the stagnation points, the speed of the flow is 0, and the stagnation streamline is the one which passes through the stagnation point, and we were able to show that psi equal to 0 is the stagnation streamline. Further, we were also able to show that the Cp distribution can be given as a function of theta, where this was 1 minus 4 sine square theta. Theta, we decided, could either be measured from this axis, the positive x-axis, or if we replace theta with pi minus theta, so that theta is measured from the front stagnation point, that also does not change the expression because of the sine square theta being there. We were also able to observe that this flow has a symmetry. It is symmetric with respect to the x-axis. So if I mark the axis, this was my x-axis and here was my y-axis. So I have symmetry with respect to x and y axis. As a result of this symmetry, we were able to observe that the drag on this body is 0 and the lift is also 0. In fact, the drag being 0 for a mathematical model versus it being substantial measured in experiments, led to the concept of D'Alembert's paradox. This was observed by a French mathematician, and then later it was resolved by Prandtl by proposing the concept of a boundary layer, which said that in a viscous flow the drag will not be 0 because you would get skin friction as well as flow separation arising out of viscous effects. So that's for a stationary cylinder. Now we want to model a rotating cylinder. So the flow that we want to look at is a cylinder which is rotating with a certain speed, let's say omega, and placed in a uniform flow. R is the radius of the cylinder, and I can talk about a non-dimensional parameter alpha, which is given as omega times r. So this omega times r gives me the tip speed of the cylinder, and it is non-dimensionalized with u. And I want to ask myself a question, that what happens to the flow as I increase alpha from 0 to a reasonably large value. Alpha equal to 0 would again give me back a stationary cylinder. Okay? So that's the mathematical model I want to construct. And I want to stay within the regime of potential flow. Right away what occurs to me is that if it is an inviscid flow and I spin the cylinder, the outer flow does not even feel it. Okay? So truly speaking, so I'll write this down, that truly speaking cannot model this with an inviscid flow. As I said, if the flow is frictionless, then the cylinder keeps spinning and the flow doesn't even know about it. Okay? But we want to see, is there any other way that we can model, maybe not in the entirety, but at least some aspects. Okay? So let us look at if we impose the potential flow for a cylinder with a free vortex. So can we use a free vortex to model at least some aspects? So what we are going to do is, we are going to now do the following. So we will superimpose uniform flow with a doublet and with a free vortex. So we have already modeled the uniform flow and doublet. This is the stationary cylinder. For the free vortex, we have already seen what are the phi and psi, the potential and the stream function. Let me remind you. So if I talk about phi and psi, then phi is given as gamma theta by 2 pi, and psi is given as minus gamma by 2 pi natural log of r. And of course the sense of gamma we already know. If this is my circular cylinder and I want to put a gamma, then this is a positive gamma. If I take a clockwise gamma, then I would have to put a negative sign here in both the, so I would have to replace gamma with a negative gamma, and then the signs would be taken care of. Okay, so the proposal is that now for the combined flow with a free vortex, I will take the phi for a stationary cylinder and superimpose on it a free vortex. So therefore, the phi that I get is u times r and 1 plus r square by small r square cosine theta, and I add to it gamma theta by 2 pi. Similarly, for the stream function, I am going to take u r 1 minus r square by r square sine theta, and then I add to it minus gamma by 2 pi natural log of r. Let us remind ourselves that phi and psi, they can be, you can add or subtract a constant out of them, and that will not change the velocity field because it depends on the derivatives. So in that spirit, let me add a constant to this so that I replace r with it non-dimensionalized with capital R. And this would give me some advantages in the sense that my stagnation streamline would become a zero streamline. Okay? Otherwise, it would be a non-zero streamline. So there is no really loss of generality by adding this constant. The next step is to determine the velocity field. How do we do that? So first I represent my velocity field as VR ER plus V theta E theta. Okay? And let me remind you that that can be done using this coordinate system. So if this is my angle theta, then if I am interested in the velocity at a point r from the center, then I can add a coordinate system. So this is a unit vector ER, and correspondingly I would have a unit vector E theta, and these are my velocity components, the radials and the tangential. They are given as following. So VR is del phi del r, and V theta is 1 by r del phi del theta. Let us work these out. So I can actually write down the expressions for VR and V theta in terms of the stream function also, but I will refrain from doing that. You can do that as a homework exercise. I want to minimize the math here and focus more on the physics. Okay, so let us calculate VR. So that would be given as u. So I would get this 1 here minus r square by small r square and cosine theta. And for the V theta, I would simply get again a u, and so minus u 1 plus r square by small r square sine theta, and from this one over here I would get a plus gamma by 2 pi small r. Let me call these as equations 1 and 2. So I already now have a model of a circular cylinder, and on it, so this is a circular cylinder in a uniform flow, and on it I have superimposed a free vortex. Okay? Alright, the first exercise that I want to do now is find my stagnation points. At the stagnation point, my velocity is 0, so V vector is 0, which would really imply that VR is 0 and V theta is 0. Okay? So let us see what the first equation tells me. The first equation tells me that 1 minus r square by small r square cosine theta is 0. Okay? And this actually gives us two conditions. This equation can be satisfied either I have a stagnation point lying on the surface of the cylinder, so that would imply R is equal to capital R, or my cosine theta is 0, which actually would imply that my theta naught is pi by 2. Let us call this condition A and this as B. Let us see what V theta equal to 0 tells us. V theta equal to 0, if I put it in this expression over here, it implies U times 1 plus R square by small r square sine theta plus gamma by 2 pi small r is 0. Okay. So, by solving for this equation equal to 0, I should be able to calculate the values of r and theta. Now, I already know that for a stationary cylinder, my stagnation points, they lie on the surface of the cylinder. So, r is equal to capital R. So, let me first try that condition. So, let me call this as C. So, I am going to try A, which is my stagnation points lie on the surface of the cylinder, and then my C would imply that I have this as 2, so twice U, and let me replace theta with theta naught to denote the stagnation points, plus gamma by 2 pi r, because now small r is equal to capital R, and there is a negative sign somewhere which I missed. So, this should have been a negative here. Yes, this was a negative here. So, this is minus 2 and this is 0. And this implies that sine theta naught is gamma by 4 pi u r. Okay. Let me call this as condition D. Sine theta naught has to be less than or equal to 1, okay, at least the modulus of it. So, note that sine theta naught equal to gamma by 4 pi u r holds for gamma less than or equal to 4 pi u r. So, if I start spinning my cylinder, okay, for gamma equal to 0, I would get the stagnation points at sine theta naught equal to 0, and that would actually imply 0 and pi, okay, the two values, just like a stationary cylinder. As I keep increasing my gamma, then my sine theta naught becomes finite, and it would reach a limit when sine theta naught is exactly 1. If I increase gamma beyond that, then I would have to go to another condition. So, then I cannot use r equal to capital R, then I would have to use the condition B, and we will talk about that in a minute. So, let us first study this case. Okay. All right. So, here is what the flow would look like. So, let us draw the streamlines. So, this is my circular cylinder, and I have here a certain gamma, and this gamma is less than 4 pi u r. In that case, my streamlines would look like this. So, first I mark the stagnation points. The stagnation points are at theta naught and of course pi minus theta naught. This is how a streamline would look like. And over here. This streamline is very interesting, okay, on the surface of the cylinder. Between the two stagnation points on the upper surface, they go in the clockwise direction, and the ones on the lower surface, they actually go in a counterclockwise direction. And I am not going to draw the streamlines inside the surface of the cylinder. So you must be wondering how I drew these streamlines. Well, so then the formal step would be that after identifying the stagnation points, I first get the equation for the stagnation streamline. So first I calculate what is the value of psi at r equal to capital R and theta equal to theta naught. So let's do that. So I would take this expression for psi and substitute in it these values. So let's put small r equal to capital R. So the first term disappears, and again if I put small r equal to capital R, the second term also disappears. So this is 0. So at the stagnation points I get psi equal to 0. So the stagnation streamline would be simply the psi equal to 0 line, and let me write that expression for you. So it would be simply ur times 1 minus r square by small r square sine theta minus gamma by 2 pi natural log of r by r equal to 0. This represents the equation of stagnation streamline, and you can see that the circle itself would be a streamline, okay? And the other equations which hit the streamline, if you plot these, you can use MATLAB or any other tool, you should be able to get these streamlines. Okay, let's see how the flow has been modified compared to a stationary cylinder. For a stationary cylinder, these stagnation points were lying on the x-axis. Once I start imposing a gamma, which I am trying to model a spinning cylinder, and mind you, my gamma is actually this. This is my positive gamma. This gamma moves the stagnation points upward, okay? And you can see now the flow has actually lost the symmetry. So I am still maintaining symmetry about the y-axis, but I have lost symmetry about the x-axis. Consequently, if I look at the drag, which would be with respect to the symmetry along the y, the drag is still 0, but I am going to have a certain lift force because I don't have symmetry about the x-axis. So let me show you the convention for lift and drag. Typically, if I have any object and I place it in a flow, then my drag and lift forces are defined as the force in the direction of the free stream is called the drag, and normal to it is called lift. Okay? So we will shortly see, and we will work out the pressure, that for this flow the drag is still 0, but it would generate a lift. Okay? All right. So that's as far as my gamma is less than 4 pi ur. As I keep increasing my gamma, a point would come where these two stagnation points. Let me call them S1 and S2. They move further up and reach the shoulder of the cylinder, and at that point I would get a single stagnation point. Let me draw that picture also for you.